In this video, I want to take a look at the integrals of vector functions. And if you liked integrals in Calc 2, boy, have I got some good news for you. Because the definition that we have of how to integrate a vector function looks like this. I'm giving the vector function here in R3. If it was R2, I'd just have two coordinates. But the integral of a vector function, R of t dt, is given by the vector function, which is the integral of all the components. So integrate the x component, integrate the y component, integrate the z component, and put those all as a vector. And so you get a vector function out of it. This is essentially doing the antiderivative. We had the definition of derivative in a previous video, and this is just going backwards. Now notice when you do an antiderivative, you'll have plus c's. You'll have a plus c here, you'll have a plus c there, and you'll have a plus c on this one. So they might be three different constants. Anyway, and then the definite integral is just the integral from a to b of r of t dt is integrate each of the three pieces and plug in the two endpoints and subtract, right? I mean, this is the way we did definite integrals in Calc 2. One quick example. Here we go. My r of t is t cubed, comma sine t, comma 1 over 1 plus t squared. And so to integrate that, I would just integrate each of the individual components. T cubed integrates to t to the fourth over 4 plus constant 1. Sine of t integrates to minus cosine t plus constant 2. And 1 over 1 plus t squared integrates to the arctan of t. I'm missing an of t there. Yeah, that's better. Arctan inverse of t plus c3. Now, you could leave it like this. I just want to point out that sometimes the way people write it is they notice that, hey, let's take all the functions part of it here that we just got from the integrals here, the antiderivatives, and take those constants and write them out here as a single vector. So it's like adding that vector. And so sometimes you'll see this as, you know, just integrate each piece. The t cubed becomes t to the 4 over 4, etc., and then write plus c out on the end. But remember that c out on the end is now a vector c with three components to add into each of the three components you have there. Okay. Now, this is pretty straightforward. However, this is not actually the definition given by many other textbooks. Right? For instance, the definition that I'm used to seeing for the indefinite integral of a vector function looks a lot like the definition that you see in Calc 2 for the indefinite integral. That is, you take the interval from, you're integrating on the interval from a to b, that's t equals a to t equals b. And so you take that interval and you cut it up into a bunch of little pieces, and in each piece you grab one particular value and you plug that, so that value I'm going to call in the ith subinterval, it's called ti star. So you're taking ti star and plugging it into r to get the function value at that time, and then you multiply it by the width of the interval, which is delta t, which is b minus a over n for this one, right? So b minus a is the length, you cut it into n pieces. So you do that, and then you add them all up from t equals 1, or from I equals 1 to n, and then you take the limit as n goes to infinity, and you look at what that is to get what the value is. That's generally the definition that's given for the definite integral of a vector function, and then there's a theorem that proves that it's equal to what we gave as the definition above. Okay. This is an interesting thing, though, because the notion of the definite integral in Calc 2 is very closely related to calculating area. And it's like, are we calculating area under a parametric curve or something like that? It's like, no, actually, no, we're not. The reason that in Calc 2 it's interpreted as area is because this part right here, this f, it would be an f of ti star or xi star, whatever it was there. But this is essentially considered a height function, and then the b minus a over n, or the delta x, in this case delta t, is interpreted, you got a height function, and then you're multiplying by a little bit of width to get a little rectangle, and you're calculating the area. So the geometric interpretation is very nicely recognizable as area. Now in this case, this isn't a height function, this isn't just a number, this is a vector. But we know what it means to take a vector times a number, you're scaling it. So let's take a quick look at a picture here. So if I had, let me just take a pretty simple vector function. It's just going to be this line. And I'm going to integrate from, this is where t equals a, and I'm going to integrate all the way down here to t equals b. Okay. So I would cut that up into a bunch of pieces, and so over here I'm going to graph the results. So starting at t equals a, that's this vector right here. Now, if you take that and then you multiply it by that little delta t, it just scales it down. So what I'm doing is I'm starting off at 0 with a tiny little vector. Come on now. I'm starting off with a tiny little vector parallel to this one that I drew here, r of a. And then I look at the next value of t. So then I'm going to take this vector right here and add it on to that one. But again, it's scaled down by delta t, so it's not that length, it's shorter, right? And then I do the next one. And the next one, right? And eventually, I already turned too much. Right? At this point, I should be pointing straight up over here. I should be going straight up. And then I start turning off to the side as I add those on. So it turns off to the side and off to the side, off to the side. And eventually, it starts pointing downhill a little bit. So I start going down. And then the last one would be right here. So each of these little vectors is supposed to be one of these vectors scaled down by a factor of delta t, b minus a over n. Right? And the net result is you're adding them all up. And we know how to add vectors. That's why I was putting them tip to tail here, is because I have the first one plus the second one plus the third one plus the fourth one and so on. So the net result is this vector right here. So the integral of this straight line vector function is, so the definite integral from a to b is this vector right here. But also what I can see is if I, rather than stopping at b, if I stopped at any point in between, I would just stop at some other point here. And this little sum of tangent lines, essentially, little tangent lines, is actually describing the curve, which is the indefinite integral of that vector function, that straight line vector function. So you're not calculating area under a curve with this. You're adding up a bunch of little tangent vectors to create the curve for which those are the tangent vectors, right? That you're finding the antiderivative. And when you do a definite integral, you're just saying first point minus last point, connect in between. So anyway, there's integrals of vector functions.